viewers, my name is Darlington Okoka and I wish to welcome you to the Delwit Electrical YouTube channel. In our episode today, we are going to be continuing from the previous class in which we talk about resistors in series. But today, we shall be talking on resistors connected in parallel. Now, what does it mean when resistors are connected in parallel? It means that the potential difference across all resistors in the circuit are all the same. That means from the circuit diagram we have on our screen, we see that the voltages, the PD on node A of R1 is the same as the PD on node A of R2 is the same on node A of R3. That means all of them have the same voltages across them, but different current flows through them. So we can see that from Ohm's law, where we have V is equals to IR, it then states, you can now see that since different currents now will now flow through, we have from R1 we have I1, R2 we have I2 flowing, current I2 flowing, R3 we have current I3 flowing through it. So in that case, we can say that our V is equal to IR, equation 1 from Ohm's law. For V1, we have I1 R1. For V2, we have I2 R2. For V3, we have I3 R3. So that's our equation 2. Now, if we make I1 the subject of the formula, since it's the same voltage that flows through the entire circuit, from equation 2 now, we can now have V over R1 for I1. For I2, we have V over R2. For I3, we have V over R3. This is quite easy because we have concluded that different current flows through different branches, while same voltages across the node. So our equation 1, our equation 2, our equation 3 is what we're going to use to form our equivalent circuit subsequently. Now, what is the total current in the circuit? From the circuit diagram, we see our I will now be the summation of I1 plus I2 plus I3. That is to say, we've gotten our I1 to be V over R1. We've gotten our I2 to be V over R2. We have I3 to be V over R3. So, since V is across, we can bring out V and put 1 over R1, 1 over R2, 1 over R3 in bracket. Now, we can now see that our equation 5 gives us what our I will look like. But from Ohm's law, we know that V is equals to IR. Making I the subject of the formula, we have V over R. If we substitute equation 6, making I the subject of the formula, into equation 5, which is our what our I in the entire circuit is, we now say our I is equals to V over R. Our V will now be 1 over R1 plus 1 over R2 plus 1 over R3. If we divide both sides by V, we now have 1 over R, which is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Invariably now, our R is equal to the equivalent resistance in a parallel combination of resistors in a circuit. So if we have n number of resistors in parallel, that means our 1 over R equivalent will now be equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn's number of resistors. So we should always note that our equivalent resistor is always smaller than the resistance of the smallest resistor in parallel combination. One thing that will come to mind is that because it's usually very difficult to work with 1 over R, 1 over R, 1 over R, there's a value that we call conductance and it should be represented with G. It is the inverse of resistance. So instead of us to represent this, our R equivalent in equation 8, we will therefore have, since our 1 over R is conductance G, we will now have 1 over R, which is G, will now be equal to 1 over R1 is G1, 1 over R2 is G2, 1 over R3 is G3, 1 over Rn is Gn. So G equivalent will now be equal to G1 plus G2 plus G3. So most times in parallel circuit, it's easier to work in conductances than to work in resistance. Now note, if all resistors in the parallel circuit has the same value, That means if R1 is equal to R2 is equal to R3 is equal to Rn, which is equal to R, then our R equivalent will be equal to R over N number of resistors in the circuit. What do I mean? If we have R1 is equals to 2, R2 is equals to 2, R3 is equal to 2, and that you can see that 2, 2, 2. So 2 over the total number of resistors is our R equivalent. So there's no need for you to start calculating any other thing again. You just divide by the total number of resistors, and that gives you your R equivalent. Then number 3, one thing you need to put there, if there are only 2 resistors in parallel, it's very easy. Our LCM will help us solve that. So there is no need for you to do any long calculation. We have an easy way to get that. It's the product of the 2 resistors divided by the sum of the 2 resistors will give you your equivalent resistance. So let's look at how it works. Now, 1 over R equivalent is equal to 1 over R1 plus 1 over R2. That means we have only 2 resistors in the circuit. So finding the effective LCM, we now have R1 plus R2. You have R1 plus R2. So invariably, this is what we get when we have the LCM. Now, by the time we cross multiply, we will know that our R equivalent now will be equal to R1 plus R1 times R2 all over R1 plus R2. So in summary, all circuits connected in parallel has the following characteristics. The moment you see that any circuit is connected in parallel, or you want to assume, or you want to testify, or you want to have it in mind, or you want to confirm that this circuit is connected in parallel, what you need to know is that the potential difference across all the resistances is the same. If you have 10 resistors, the PD across all the 10 resistors are the same, in as much as they are connected in parallel. Now, the current flowing through each of the resistors is different. So the current through R1, current through R2, current through R3 is different. Finally, the total current in the circuit is the sum of the individual current across each resistor. So if you have I as the total resistor, the current across R1, R2, R3, when you sum them together, it will give you source current. Now, we also know that the branch current, the branch power, and the branch conductances are all additive. So you can add them together and get what you want as your value when you've added them. So this is a summary of what a parallel circuit is, and I believe you've been able to get 1 or 2 things from this. So we're going to do the practical section now. We're going to see how when resistors are connected in parallel. Our resistors here are going to be 60-watt bulbs, the incandescent bulb, because if we're going to use LED bulbs, you might not see visibly. So when we use the incandescent bulb, you'll be able to know that by the time the same voltages flow through it, you will see that the illumination will be the same. But you remember when we did our series circuit, when we use the same voltage source, we saw that there's voltage drop across, which reduces the illumination. So let's try this practical out. Now, welcome to the practical section of the parallel connection of a circuit, resistors in parallel. Now, as you can see on the circuit design, we are going to have a source. So on this particular lamp holders, which is serving as our resistor, you know, in our parallel connection, we are saying that the same voltage that comes in here is the same voltage that comes in here, is the same voltage that comes in here. So they are connected in parallel, having the same voltage. So in parallel connection, your live and neutral is here. The same live and neutral comes to here. The same live and neutral comes to here. That means on the same node, they are having the same voltage. So let's see how the connection will be done. All right. So now in this connection now, we're going to be using a stripper. It's both a stripper and a cutter. We have a plier and we have our screwdriver. So the stripper is actually used to strip your cable. this is the parallel connection. You could see that the neutral is connected to this neutral, is connected down to this neutral. The live too is connected to this live, is connected to the live. So they have similar nodes. It's just the nodes are looped together. So the voltage at node A is the same as the voltage at node B is the same as the voltage at node C. So let's connect the bulb and see how the illumination will look like. Now you can see that the lamp holders, which are the R1, R2, R3, they've been connected. So we're going to be using a 100-watt bulb. We'll connect it across and see if the voltage here is equivalent to the voltage here, as equivalent to the voltage here, as described on the parallel connection. So let's put the 100-watt bulb here. Put this other 100-watt bulb here. And put this 100-watt bulb here. So let's check the illumination if the voltage is constant. So it has been connected. You can see that the voltage here is equivalent to the voltage here, is equivalent to the voltage here. If you had looked at our last week lecture, you will discover that the voltage here for the series is less than the voltage here, is less than the voltage here. But this is parallel connection. You can see that the voltage level is the same. So that's parallel connection. This is the same principle is applicable to all other parallel connections. So when you are doing your calculation, what comes to your mind is voltage in parallel is the same, while current changes. So I believe this topic we've treated resistors in parallel have been very educative. If you have any questions, feel free to comment on the comment box, and be rest assured that I would attend to every question on the comment box. So please click on the subscription button to get notified on whenever new videos are being posted.